field, the potential energy, and the potential. Okay? And they're related, they're very symmetrically organized. Physics is a very well organized subject. It's very old, very ancient. It's not like biology. But so that's why I like to teach myself in the organized fashion. This is a better marker. Okay, so the force is Coulomb's law. With a K here, Q1, Q2, and the distance between 1 and 2 to the second power. At the beginning of electricity. Okay? And of course, force is in newtons, because that's the unit of force in mechanics. So that applies to point charges, small q. Okay? You want to make a representation, you know, you have one charge here, another charge here. This is the distance. So Q1, Q2, and you're dealing with the force between them, and we don't put signs on this law. It's absolute value. So you are responsible to know if the force is attraction or repulsion. That's the only possibility. And you know, if you have plus plus, the force is repulsion. So they get away from each other. If you have minus minus, the force is also repulsion. They get away from each other. But if it's plus and minus, they attract. And this is the way, this is the way to put, when two things attract, that's what you do, right? You put the vector on the charge. Not the head of the vector, but the tail of the vector on the charge. So, I haven't told you what is the sign of these charges, so you cannot decide if it's attraction or repulsion. Okay? So, if they are both plus, let me put this one plus and this one minus. So, if I ask to draw the vectors, the force vectors, what do you do? The vector on Q1 and the vector on Q2. They have to attract. So they have to point towards each other. This one is going to be attracted by the other one, and this other one is going to be attracted by the first one. And the forces are identical. Eh? This force is the same for Q1 and Q2. In fact, by Newton's third law, you know, the force on 1 produced by 2 is equal to the force on 2 produced by 1. If you want to put a negative sign here, you can put it because they're opposite. They're opposite vectors in the opposite directions. Okay. So Newton's third law is applicable, and it has to be applicable even in repulsion. This force and this force are equal, and they are opposite also. This goes to the right, this to the left. So Newton's third law is very important and valid in electrostatics, the very beginning. Okay? In Coulomb's law, it applies. Second concept, the electrical force per unit charge. Now here's the problem starts, because there's only one charge. Which one is that? Why did they want to do that? Why don't they just live with Coulomb's law? Well, for some more complicated situation, it's easier to think that one of them, whichever, select this arbitrarily, is producing force, is producing an electric field all throughout. Okay? And then another charge, if you put another charge in this region, is gonna experience a force. It's the same as before. You need two to tango. But now the emphasis in one of them, which is gonna be called the source, arbitrarily, and the other one is gonna be called the test charge. So actually, in this definition, this is not the source, this is a test charge. The book actually puts a prime on the test charge. So the force on a test charge, or per unit test charge, is called electric field. Produced by whom? Another one, which is not specified. You see, here now we are just putting things. It's useful later on, but at the moment, why do they do that? Okay? It's kind of unilateral. If we need action and reaction, why they put only one? Well, let it be known that this is the test charge, and that this test charge is always positive. The book says it could be negative or positive. So, if you have a region of space, and you put a test charge here, a mosquito, I tell myself, that mosquito is positive. And then, if the force is this way, on that mosquito, the electric field is that way. The field is a vector, in the same direction as the force. So, what is the direction of electric field? The direction of a positive test charge in that region. Okay? So, now, given that definition, and I like to put 3 lines for a definition because it's just mathematics, it's words if you want. How do you calculate the field of a invisible test charge, source charge? What Q source is producing that? Well, go to this formula now. So, the only thing they have done is one of the two is going to be called test and put it down here. Okay? It's irrelevant. It could be Q1, Q2, arbitrarily. So if you divide F by one of the Q's, what do you get? F divided by one of the Q's, the result is K, the other Q, and the distance squared between your source and your test charge, squared. So the calculation of electric field of a point charge, which is called source arbitrarily, let me put it here anyway, is half of the Coulomb force. Is this formula truncated? Because you already divided the force by one of the two charges that you call test charge, and then what you get is E. Okay? So this is the definition, this is the calculation. And it's also a vector. So, but we put here always in brackets because we don't assign signs. Otherwise it's complicated because it can go to the right, it can go to the left, so there's no need to put a sign there. It might be confusing. You have to know by inspection. Okay. So, students have sometimes a problem in deciding what's the direction of the electric field. Okay. Okay. Then once you have, how many problems or what kinds of problems do they do with this? Well, we can calculate forces between charges. It could be 2, it could be 3 in a line. It could be in a triangle. It could be in a square. And then, because there are forces, you have to use vectors and components. All the x's, all the y's, and you did this in physics 1, supposedly. Okay? How complicated can this problem be? It depends on the professor. You have problems of that kind, right? He assigned homework where you have several charges. Can you tell me or ask more or less what is what? Because there it could be very complicated. I don't abuse my students. Sometimes I only put the 2 charges, which is easy. Sometimes I put 3 charges, for example, one here, another one in here, and this is the coordinate system. Okay. But depends on the professor. And there's a class of problems where they ask you, here's a positive charge, 5 nanocoulombs. Here's a negative charge, 10 nanocoulombs, and it's negative. Where do you put a charge so that the electric field is 0? Or the force, the net force on some other charge is going to be 0. That's complicated because there you have to remember everything. Let me put a negative charge here. And forget about the formula. Where do you think I have suppose the question is, where do I put a positive charge? Can even tell you the amount, but qualitatively, where do you think I should put? And there are three possibilities: on the left side, on the center or the middle, and on the right side. And to decide where it goes, you have to know the qualitative law. When do they repel, when do they attract? And a little bit of the quantitative law. The closer they are, smaller, the bigger the force. Which, without calculation, you have to know that. When these things get small, the force gets big. Okay. Can you do this? Can you tell me? Here, here, or here? And you try. For example, try here. If I put a positive charge here, what's going to happen to that positive charge? Coming from this one. It's going to be attraction or repulsion?
Repulsion.
And what does it mean, repulsion? On this guy, it means away, go away. On this guy, also goes away to the right. But we don't worry about this one. We worry about this one because we're exploring where the force could be zero. Okay, now what's this doing to that one? Is plus minus is?
It's attracting.
Repulsion.
It's attracting.
Okay, so it's gonna, let me use a different color, it's gonna pull it to the left. Now, is there any chance that these two forces are equal so that they cancel?
No.
This is 5, this is 10. Well, 5 is weaker, force will be weaker, but it's closer. The other one is going to be, 5 is less, but it's close. So whatever it loses because it's smaller charge, it gains by the smaller distance. Whereas this other one is a bigger charge, but it's farther away. So it seems that by chance I chose, the first option here is the one that you have to try. For example, if you put it here, suppose that you put it here, plus plus, repulsion. So this one will go to the right or left?
To the right.
And this one, minus plus, will be attraction. So it will go also to the right, attraction. So obviously here you will never get a zero value because both forces on the test charge are going to go to the right. And here, yes, it's going to be attracted by this and repelled by this. But this, which is a big charge, and it's closer, is going to win the battle. So never you're going to be able to equate the two forces. So apparently, only here. Have you done any problem like that? Mm-hmm. To find the 0 point of a force? Okay. The technique is, once you decided that it's here, then you call this distance x. And if they tell you that this is, 20, from here to here is 20 plus x. That's the technique, the mathematical technique to state the problem. Then x means that you put here x squared. X is something that you don't know. So for the force produced by this charge, you have to write the complete thing. You have to write 5. Of course, this has to have some value. Let's put 1. Make it easy. 1 nanocoulomb. So 5 by 1 on the top, and underneath x squared. Now, since you don't know x, you equate that to the other combination, which is this guy and this guy. That you are going to have 5, which is, this is 1. The test charge is 1. Here is 5 by 1. Here's now 10 by 1 without signs. Divided by the distance, 20 plus x squared. Wow, comes a little bit difficult. But once you have reached the equality of the two forces, this goes this way, this goes that way, and in terms of x, you find x. And that's the problem. Perhaps that's the most difficult problem in this whole collection. It doesn't need vectors. It only needs the idea of attraction and repulsion. Okay. Okay, that's an example. But the idea, I think, is not to go to detailed problems. Problems will come later. And each problem has its own little trick. Okay. Normally, what you do with this, with forces is the same as with field. The only thing is that, for example, if I put a situation like this, I can ask you, what is the force between these two charges? Well, I have to give you the distance, I have to give you the charges. You apply Coulomb's law. But suppose that and also this, you can calculate the forces between all of them. This and this, between this and this, and this. That's just routine. Normally, what they ask you is, what is the total force that these two guys exert on this, or that these two guys exert on this, the total force. Then you have to add vectors. For example, this configuration is very typical. If this is plus, and this is minus, and this is just whatever, just put plus. Let me test you momentarily. The force that this exerts on this, Newton said that the force is always between the line of centers, right? It's along the line, so it's along this line. But the direction, this guy is doing what to this guy? Attraction or repulsion?
Repulsion.
And repulsion means this way. End of story. This one also repels this one. But the question is of what happens here, is what happens here. Okay? The other guy, negative. There's a negative charge here and a positive here. So between this and this, we're going to have attraction or repulsion?
Attraction.
Attraction. So the vector should go to meet the other charge. There's another vector here, but we don't care about that. So now this guy has two forces on it, and they're equal. Well, if this is equal to this, these vectors are equal. Let's make it equal. So the two forces are going to be equal. Okay. So I have to find the resultant. And this is physics 1. Remember what you did? You find the x value of this, the y value of this, you find the x value of the other one, the x component, and the y component of this one. To do that, you have to know this angle, which is equal to this. This will be this by the cosine of the angle. This will be this by the sine of the angle. And you notice there's something that is nice. Normally by symmetry. But in this case, this is equal to that. Because if these are equal, and the angles are equal, this is an isosceles triangle, this vector, which I didn't draw correctly, are going to be equal. So the y components cancel. So, how simple? Get the x component of this, and this is identical, so multiply it by 2, and then you get the total force, which is going to be, as you see to the right, it's just twice this one. Amazing, eh? That a dipole, this is called a dipole. When you have a combination of two equal charges that are opposite, it's called a electrical dipole. It's going to produce a force on this test charge to the right. It's not going to come here or here. Yes, it comes here. I mean, it repels here and attracts here, but that combination produces a net force to the right, which is interesting, huh? So that's an example that involves going back to physics 1 to find the components, sigma x, sigma y, okay? Okay, but that's just something that you should know. So electricity is a force, so you can apply vectors to it. Okay, so this is the world of forces. Both equations are forces. Okay, and that's it. Remember that when I can ask you students, and I do, what is it? Okay, forces are in between charges, so you need two guys, Q1, Q2. But a field is only one. It's produced by only one. Where? On a field point that is empty. A charge produces a field everywhere in space. So if I tell you what is the field here, there's nothing there. Call it P, point P. So then you have to apply the formula for field. You have the distance, and you have the value of the charge, Q source, and you divide by the square of the distance. Okay? So this is something that students, but field there, there's nothing there yet. Well, the field calculation is the calculation of the value of something that is empty there. There's nothing. That's the concept of field. Region of space where electrical forces occur. It has a philosophical part, Okay, I have a force if I have two guys. If I have only one guy, I'll take away the other. Is there anything in space? Is there forces in space? Newton tells us you need two, action and reaction. They say, oh yes, the field is there, the field. Well, how do I know? Well, I'll put a test charge and you see that it's going to be certainly force, away or attracting. And the question is, if I don't put the test charge, is there a field there? Is anybody's answer? What if I don't put this charge? Is there anything there in space, in empty space? Okay. Normally they say yes. But this requires looking back at the electromagnetic waves, and so that's a philosophical point. Eh? So these two guys always take square of the distance. Now come a situation which is simpler because energy is not a vector, it's just a scalar. And the energy is simply, K again, is the force. You know how I demonstrate this to students in physics without calculus? Okay, what is energy? Force by distance, right? Work. Work is energy by travel distance. Let's call it S. Okay, call it D, call it S, call it X, whatever. So if you multiply the force by some distance, because you are moving, remember that work is when the object that receives the force, for example, when you push a cart, okay, you're moving. And when you multiply that motion by the distance, you have the idea of work. Force. If it's constant, very simple, just multiply the force by S all along. In electricity, it's not going to be the case because the force, as you move away, you have a charge here, and another one that's going to be moved away, suppose that is positive. As they get away, the force is different. So you have to use calculus to do the integration of the force of Coulomb by a distance. In other words, it's r squared by dr. When you do that integration, what do you get? 1 over r. So I tell my students that don't know calculus, listen, just multiply by r. So that's work. Then what do you get? Work is energy. So K, Q1, Q2, both charges, divided by R to the first power, because this cancels one. So the energy is just divided by R. I know this is heresy. I cannot do that. I have to integrate. But it happens that the result is as if you had multiplied the force by a distance, period. So for the sake of clarity, I just taught the student, listen, the potential energy is between two things. In fact, it's the energy of the system, okay? Divided by the distance between them to the first power. And it's not a vector, it's a scalar, and you have to put this sign. Now you have to put the sign of the charges. If one of the charges is negative, the potential energy is negative. If both charges are negative, minus minus gives plus, the potential energy is plus. Isn't that amazing that the vectors, we don't put signs, vectors which are directed, and this scalar, which has no direction, we do put the sign. We have to put the sign. The units of energy, of course, is joules, as you know. Here is Newton per Coulomb, okay, because it's force divided by charge. Okay. What if we have a system with three charges? Q1, Q2, Q3. Well, if you have a system with three charges, Q1, Q2, Q3, the potential energy is just the potential energy of these two guys. Q1, Q2 divided by R12, plus Q2, Q3 divided by R23, plus Q1, Q3 divided by R13. And it's just an arithmetic addition of all those products. So, of a system of charges is the addition of the product Q1, Q2 divided by the distance 1, 2. Okay? Whatever number of charges you have. And this is in the book. And I don't know if Professor Rodriguez is gonna or had done any problem like that. It's just electric potential energy. Electric potential energy. Because in physics 1, you study potential energy, which means gravitational potential energy. So when you talk about potential energy in physics 1, it's the gravitational potential energy, MGH. The force, the weight by the distance, MGH. So we just call it potential energy, but now we have another kind of potential energy, so we better call it differently. Electric potential energy, symbolized by the letter U. I think, no, that the book uses U. Okay, so these are easy problems. In the case of this, I can ask my students, what is the potential energy of Q1 and Q2? Oh, very simple. Q1 by Q2 divided by R12 to the first power. Instead of Q1, Q2 divided by R12 square, just avoid the square and put the signs. Okay. So potential energy calculations are not too bad, maybe not that frequent. The last factor summarizes everything. The potential alone, not the potential, not the potential energy, is by definition the potential energy per unit charge. Again, test charge, or prime, because the book I think uses prime. So this is the simplest one. How do you calculate that? Well, you have U here. If we divide by one of the two, call it test, then the potential is going to be K, Coulomb constant, by the charge that remains, the source, divided by the distance to where, since there's only one charge, to the point, to the empty point, let's call it P. Okay? So you see how the four formulas get simpler and simpler. This is the most difficult one. Take out one charge and you get the field calculation. Then again, put the two charges, but put the first power. And then take out the test charge, put it down, and then you get the potential. So there's a relationship in the sense that if you multiply this by R, you get this one. If you divide this by Q, you get this one. If you divide this by Q, you get this one. If you multiply this by R, you can go direct from the field to the potential. See, just multiply by R. As you did here, multiply by R, you get the energy. Okay? In the fancy language of calculus, the potential, since you multiply E by R, let me put it here. If you multiply E by any distance, R, you get the potential. I call this formula ED. Anytime you multiply the field by a certain distance, you get the potential. And because that distance is normally from one point to another, okay, A to B, well, we can call it potential difference between A and B. Because actually it's a potential difference because, like in gravity, okay, from here to here, where is the zero? We don't know. It's just the difference. You can call zero the ground. In electricity, the zero of potential energy and of potential is infinity. You're going to see that the problem tells you take infinity as the zero reference point. Because when this goes to infinity, yes, the potential is zero. Okay? So a charge very far away has no potential. As it comes closer, it increases the potential by this distance. Okay? So those are the four things that are in electrostatic, the four columns, the four basic concepts. Okay? Now, handling these things is your expertise. And of course, there are problems and problems. You know what I do, and yesterday a professor accused me that I had a lot of A's, my students get a lot of A's. And Darishi from Turkey, she one time said, how come you have so many A's? I said, well, professor, because I give them a good review before the test. And she said, oh, so you are like in high school. You tell them the answers before the test. You know, what's nasty. I don't give it any answers. I give them a review, period. And yesterday I was talking to Professor Rodriguez and others, Jorge Rodriguez, and the same thing. It's not good. You're giving the answer before the test. I don't know why that spread around. Okay? So, that's as much as I can say now. Then you have to practice the problems, but it's good to have the concepts clear and their structure, their interrelationships. Okay? When you get Gauss's law, actually Gauss's law is a trick to apply this to systems of charges. For example, instead of a point charge, a sphere. So now the charge in the sphere, I like to call it big Q. It's spread all around. You know that conductors try to repel the charges because a conductor is one that can conduct electricity. So if they hate each other, they're going to be at the opposite sides. So normally a conductor has zero field here, you heard that, and the charges are there. But suppose that you know nothing. What is the field? Can you imagine the field here at a certain distance r, bigger than the radius of the sphere? What is the field there produced by all these guys? That would be impossible to take each of these and add vectorially. So this guy, Gauss, who was a mathematical genius, he said, look at this equation. If instead of k